Now let us move on to the secant method. Let me use a different color pen here. So the idea behind a secant method is same as Newton-Raphson method. Okay, so we know in Newton-Raphson method, this is xi minus fxi upon fxi. Okay, but when you talk about Newton-Raphson method, generally now we have applied Newton-Raphson method to a very trivial problem. Okay, but when you talk about very complicated problem, finding derivative is a problem, because if the function is very complicated, finding the derivative of that function is also a very complicated task. So what the secant method says is, instead of finding out derivative, why don't you replace this derivative by the first order Taylor series approximation. Okay, so if you replace that, that comes out to be xi plus 1. Okay, and what is that approximation of derivative? The approximation of derivative is fxi minus 1 minus fxi upon xi minus 1 xi. So what you are going to do is you are going to substitute this here and you are going to replace it. So once you replace it, the equation becomes xi minus fx upon xi minus 1 minus xi. I think this should be I. Going to be fx I minus 1 xi. Okay, so this is the formula for your secant method. So we'll use this formula for calculating your for finding out the root of the same problem. Okay, let me copy this thing. Let's copy this to the next page. I think just paste it here. Okay, so this was the problem. Okay, so the equation is fx e raised to minus x minus x. Okay, since this is a secant method, we have to use two starting values. Okay, and I think the starting values are also given in the problem. If you see the previous page, it's x0 is 1 and x minus 1 is 0. x0 is 1 and x minus 1 is 0. So these are the starting values that is given, and this is the formula that we are going to apply. So again, I'll use a table because I find it I'm comfortable with that method. Okay, you don't necessarily have to use table, but I would suggest, because you can check your calculation, everything at one place. Okay, and you don't have to turn pages again and again, which becomes irritating when you are solving a bigger problem. So the first thing is going to be my iteration. Then the next thing is going to be my xi. This is going to be my xi minus 1, because if you see in this problem, we are using the current previous to previous. We are using two things, okay, to find out the current value, and also we are using the function function of xi and function of xi minus 1, which I think will be very helpful for us. And xi plus 1. Okay, so 0th iteration. No, okay. So the value of xi is given, x0 is given. What is x0? x0 is 1 and x minus 1 is 0. Now if you substitute these values in the function fx, you'll find out the value of fxi or fx0 comes out to be 0.63212, and when you substitute x1 I minus 1, function of x I minus 1 comes out to be 1. Okay, so now we have all the things that we need to substitute to find out the current value of x. So if we substitute all these things in this equation, okay, what you are going to get is value of 0.6127, and when you compare it with the actual value, the true value of x, which is 0.5, if I can recall, 67143. Yes. Okay, so calculate the percentage error from this and you'll find out the percentage error comes out to be 8%. Let's move on to the next iteration. So the current value for the next iteration becomes your previous value, and the previous to previous value will become your previous value. Okay, your previous value will become previous to previous value. So basically what you have to do is this xi or x0 will become this. So you just have to copy this here. Okay, and you have to copy this here. Okay, so the current value will become your previous, and your previous for the previous iteration will become previous to previous value. Okay, it sounds a bit difficult, but it is not. You just have to, if you think x minus 1 and stuff, you'll realize what I'm talking about. Anyways, but to calculate the xi plus 1 for the next iteration, I need xi minus 1. I also need xi. I have value of xi minus 1 and xi. So once I substitute xi in my function, if you substitute that, you'll find out the value that you're getting is 0.07081, and the value of xi plus 1 that you'll be getting is 0.56384, and the percentage error comes out to be 0.58%. Okay, so again you're talking about true percentage error. It's better to get the true percentage error and very close to 0. It is 0 point, but still I think we can go to another iteration here. So let's go to the next iteration. Again, this will become your previous, your current will become your previous. 5, 6, 8, 4. Your previous to previous will become your previous. 6, 1, 2, 7. Or maybe I should not talk in terms of previous. I can say your xi plus 1 becomes your xi, and your xi becomes xi minus 1. So as simple as that. If that happens, then your function fxi, your fxi will become your fxi minus 1. That is 0.07081. Now again, to find out the value of xi plus 1, we will have to substitute these three things. So obviously we'll need this thing. So what you can do is you can just substitute this again here in your function. You can get the value of fxi. The value of fxi comes out to be 0.00518, and once you substitute everything, you'll find out the value comes out to be 5617. So 0.0040004%, which is very, very close to 0. Okay. So this was your secant method. I hope you guys liked it. It is simple. Draftsman and secant method is very simple. This, if you see here, we dealt with just a single equation. Okay, but in real life you'll have n number of equations. So when you encounter n number of equation, how you are going to solve? Okay, so we are not going to discuss that in this lecture. I have kept a separate lecture for that. That is system of equation, where I am going to solve non-linear equation, and I'll be using Newton-Raphson method, okay, or also secant method, if I'm not mistaken. Yes, to solve system of linear equations. Oh, sorry, non-linear equations. And so I think this is it. So this is very good, easy, yet powerful stuff for finding out roots of non-linear equations. Okay. So that'll be all for this lecture, and I'll meet you in the next lecture. Okay. Thank you very much.